Okay, Homestretch of the 2016 exam now. Just the waves and optics questions to go. So we've got one of Pete's lovely pictures here. It's a wave. What does it say? It's two travelling waves, A of x of t, solid line, and B of x of t, dashed line, at time t equals 0.15 milliseconds, where x is the spatial coordinate in meters. So this is a snapshot at a particular time. You can see at this time the two waves are not in phase. Okay. Now, figure 2 shows two travelling waves, A of x and t, which is c sine kx minus omega t, and B of x of t, c sine kx plus omega t, with wave number 6.283 radians per meter. Now, angular frequency 2.094 times 10 cubes radians per second. At a particular time, t equals 0.1. What is the phase difference between the two waves in radians? Okay. Phase difference, okay. One wavelength is equal to 2 pi radians. Alright. So, what is a wavelength? Well, the wavelength, as we can see, is exactly 1 meter. It's been given to us already there. 2 pi radians per meter. So one wavelength is 2 pi per meter. Okay. So wavelength's a meter. So what's the difference? The difference looks like it's exactly 0.1. So therefore the phase difference is 0.1 over 1, the full wavelength, times 2 pi, which is equal to 0.6283. That one. Okay. Consider the waves in figure 2. The resultant wave arising from the superposition of these two waves will result in destructive interference to form nodes for the following conditions. Okay. At particular values of t where the troughs in one wave align with peaks in other. See that particular values of t? No. Okay. Nodes are places where the amplitude is always 0, not just at a particular time, so no. At all times of t for particular values of x, such as approximately 1.5 meters, well, let's look at 1.5 meters, okay? So if we look at 1.5 meters there, we look and we see that 0 is about here. And so it does look at this stage as though A, the solid line, is about the same distance above as B, the dashed line, is below. So at this point, at least they do add up to be 0 at this instant, right? So that's a maybe. At all times t for particular values of x, such as approximately 1.12 meters. Okay, 1.12 meters. No, both of them are above the line. They'd add up to something up here. So that's not going to be destructive interference with a node. At particular values of t, again, a node is for all values of t, not particular values of t. At all times t for particular values of x, such as approximately 1.25 meters. 1.25 meters. There again, that's 1.25 meters. The two add up to give a huge amplitude. So no, it's not. Okay, and it's not 1.12. And 1.5 is about right. Now note thing, we're given the angular frequency kx minus, kx plus. They've got the same amplitude, they're travelling in opposite directions. So if there's a point where they add up to be 0, they will always add up to be 0. So that is the right answer. B. Now, a cylindrical tube of length L has one length open and one length closed. Here it is. What are the wavelengths of the three longest wavelengths that can form standing waves in the tube? Well, let me draw them. First of all, this one, that's the fundamental. It's a quarter wavelength. A quarter wavelength equals L. Let me draw the next one. I'll give myself more space this time. And this one is 3/4 wavelengths equals L. And lastly, the next one, and try not to make the tube any longer, we need to get, it goes like this, and now we have half a wavelength, 1 wavelength and a quarter, so that's 5/4 wavelengths equals L. Okay, so this is lambda equals 4L, this is lambda equals 4L over 3, and this is lambda equals 4L over 5. Okay, that one. Beautiful. I mean, basic principle, closed must be a node, open must be an antinode. An 8 kHz sound wave is emitted in all directions from a point source. At what distance from the source does the intensity ratio between successive wave fronts drop below 1.01? Oh my god. Oh, that is hard. Okay. Ugh. We start with I is equal to some value over d squared, because intensity always drops off with the square of the distance. Okay, and now lambda, c equals f lambda, therefore lambda equals c over f, and in this case is 330 over 8 kilohertz. .04125 meters. Okay, so that's the wavelength. So we require I of d over I of d plus lambda to be less than 1.001. That is I naught over d squared over I naught over d plus lambda squared now is less than 1.001. The I naughts cancel out and we end up with d plus lambda squared over d squared is less than 1.001. Okay, d plus lambda squared, put in brackets, yep. Maths, don't you hate it? Okay, so d plus naught, well, okay, okay. Let's just use equals for time being. We get the, so we get d squared plus 2d lambda plus lambda squared is equal to 1.001 d squared. Bring that over there. So therefore, if we take, rearrange, we're going to get 0.001 d squared minus 2 d lambda minus lambda squared equals 0. Okay, and I suppose we just multiply this by 1000, so it becomes d squared minus 2000 d lambda minus 1000 lambda squared equals 0. And I guess what we do is just plug in some values and see how we go. So d squared, let's try 82.5 first. 82.5 x squared minus 2000 times d 82.5 times lambda 0.04125 equals minus 1000 times lambda squared, which is 0.04125 squared equals, and we get, okay, so 82.5, we get minus 1.70. Okay, and it seems pretty close to 0 to me. If we try it for 41.3 meters, we're going to get try again, John. 41.3 squared minus 2000 times d, which is 41.3 times 0.04125 equals minus 1000 times 0.04125 squared equals, and we get minus 1703. Minus 1703. That seems good, that seems bad. Notice that B can be crossed off because the intensity cancelled out here. Okay, yeah, no. 0.041, I really don't think that's going to work. Okay, we can try it. 0.041, that's just the wavelength. That's just a silly idea. That's closest. That'll do. I reckon that's the answer. Why isn't it exact? Well, because that's not exact. Okay. A pulsed light source of temporal width 10 picoseconds and a light detector are placed 1 meter above the surface of the water surface of a swimming pool of depth 2.5 meters. The pulsed light is shone vertically down onto the water, and vertical reflections from the upper surface of the water and the bottom of the pool are detected. The wavelength of the light is 389 nanometers, and the refractive index of water at this wavelength is 1.33333. Estimate the time separation. Okay, time separation, easy peasy Japanesey, let's go. So, one light goes down, comes back up like that. Other light goes down, comes back up like that. So it travels an extra distance of 2.5 meters down and 2.5 meters back, so a total of 5 meters. Its speed is equal to 3 times 10 to the 8th divided by 1.333. Therefore the time it takes is equal to distance over speed, 5 over 3 times 10 to the 8th over 1.333, and calculator. 5 divide brackets 3 exponent 8 divide 1.333 close brackets equals 2.22 by 10 to the minus 8 seconds equals 22.2 nanoseconds. That one. Okay. Some are so easy, some are so hard. Last question. Consider three materials, each of different refractive index, through which a beam of visible light is passed. Which of the following statements is true? The frequency of the radiation is the same in all three materials. That's true. The speed of the radiation is the same in all three materials. No, it's our definition of a refractive index. The speed is different. The wavelength is the same. No, it won't. They get squished up as they go slower. The ratio of the speed to frequency is the same in all three materials. Well, ratio of speed to frequency is C over F, which is equal to lambda, and we said that the wavelength wasn't the same, so that's saying the wavelength is the same. It's not, no. Total internal refraction will occur at each boundary between the materials, only for certain situations, not at all angles. No, nothing, it's just the frequency. That's the one that has to be the same. It's the same because if it wasn't the same, then there would be a build-up of wave fronts in a particular material, and they would get closer and closer and closer together, and they don't. The same number of wave fronts must go past every second throughout the whole system. Done.